Right. Hey guys, let's get started. Okay, so today's the first lab, and I will go over basically how what we're going to be doing, the problems. I'll demo some of these, kind of like do a little bit of a demo, and then give you a little bit of time to work on it, and then we'll move to the second problem and so on. Okay, so I'm recording the session, but if you follow along, you should be able to do this lab pretty much. Should be able to complete at least 4 out of 5 problems, and then the fifth one is just it's not going to be difficult. All right, so let's go over to content. Table of contents here. All right, so we're going to be working on this module, right? Secret key encryption. Okay, that's the very first one. I haven't gone over any of the theory yet. Okay, I will do that next Tuesday. I'll start formally defining a lot of these primitives, as they're called. But today it's just kind of, we're just, playing around with encryption. You probably want to, we want to motivate what we're doing, right? So we're going to encrypt some things, an image, some text, and then we're going to play with it. Okay, and then I say that next week also I'll do a Python scripting example, and that's just kind of to get you guys, thinking about Python. It's kind of more of a catch up, if you will, or review. All right, so which will be this one, a Python substitution cipher. So this is obviously the pre-modern techniques, but it's a good exercise, to think about cryptography. All right, so you're going to need the following materials. So if you can see, I already created the link for the assignment, so you can take a look at that. I'll start with that. And I usually repeat this a lot, so I'll have like a Word document, and I just copy what's in the Word document here. So there will be it's repetitive sometimes. But basically, as I said, I may give you a lot of material sometimes, a lot of things to read, PDFs, etc. You should go with what I say here, and I'll say usually, 5 problems, something like that. All right, so this is your first assignment. So let's take a look at some of the basic things of how I set this up. So let's just work. Yeah, here, I guess. Yeah. So today is the 22nd, and this is due a week from today, right? So that's your soft deadline. Okay. So if you don't submit by that time, it's going to mark it as late. That doesn't affect your grade, but it's like a warning. You're already late on your homework, right? And then I have a hard deadline, which is usually Saturday or Sunday. Pay attention to that. It should be Sunday, but sometimes I make the mistake and click on Saturday, okay? So just watch out for that. But I usually try to mark Sunday as your hard deadline. All right, so, and the idea is, so I assigned the homework today. Soft deadline is due next Thursday. You can ask questions about the lab either today or next Thursday. Those are your chances. And then, make sure you submit. But like I said, I usually try to demo these. And so if you follow along, you should be able to complete it. Okay, so that's basically the idea. All you have to do is submit a lab report, as I explained. Take a Word document, put in the problem number, some screenshots that show evidence that you completed the task, and maybe 2 or 3 sentences to summarize it. Okay, and that, if you understand what is being asked, then you should be able to answer the question, right? So that's the key. So, understand the problem. All right, so let's take a look. You can see there's 5 problems, and I will demo most of these. So number 1, encryption using different ciphers and modes of operation. So we're going to take a text document, a text file, a sentence or something, and we're going to try to encrypt it and just see what happens using OpenSSL. So we're not writing any code for this lab. Problem number 2, we're going to do an encryption of an image. And we're going to do something like DES or AES, but we're going to try out different modes of operation. And we're going to see that some might be more secure than others, right? And that's the idea. And then don't worry if you don't understand right now why, we're going to look at these algorithms, right? So that's the whole idea, is that, ECB is an algorithm. It's like a way that you do it, for loops and if statements and things like that. So it makes up the algorithm. Then we're going to look at padding. This should be a very straightforward example. I mean, the problems today are very easy, right? basically the idea is, is padding added to complete the blocks because the block should be of equal size. So we're going to take a look at that. And then number 4, thank you. Did everyone sign in? Right. And then problem 4 should be corrupting the cipher. So that's the idea that you encrypted the file, you sent it over the internet. We know that there's noise on the internet. What happens if one bit is flipped? What does that do to the encryption? Does it ruin the whole thing? How does that work? Okay, so we're going to play with that idea as well. And then you can see here number 5, I've said this before, really to understand cryptography, you have to work with someone and you have to send the messages. So this is about, securely communicating, right? So I ask you questions, or I'll ask you to do demos, with your partner, and then you'll say, I'll say, okay, send them the key, but send it securely. And you need to understand what I mean by that, right? And so you need to show me that actually the exchange of the key or the exchange of the message was actually done securely. Okay, so that can only be done really if you're working with someone. So we'll start with that today. This is a very easy problem. Find a partner. So work with a partner and send them a file via email. Also, that's going to be our way of sending things via email. You can just use your PNW account, your Gmail account is fine. So make sure you achieve perfect confidentiality. Okay, so that's the key thing, right? So I'm already throwing the principles at you, and you need to understand what I mean by that, right? So make sure you achieve perfect confidentiality. In your report, indicate your partner's name so I can look at their report when I'm grading them. Does that make sense, guys? Any questions? So you'll encrypt something, a message, and you have to send it and achieve perfect confidentiality. And you need to tell me how you did that, actually. Okay. So that's, what this problem does is it makes you start to think about some of the, the hurdles, right, that you have to address in the problems. Okay. All right. So that's the 5 problems. So that's basically how it works. I usually have a Word document, and it should pretty much say the same thing, but it's for my own reference. And it might have a little bit more information. Yeah, it has a little bit more information. So certainly read through this as well, but it should be the same 5 problems. I'm usually tying these to some bigger document like the PDF, okay, which has a lot of information. So, secret key. In this task, we will play with various encryption algorithms and modes. You can use the following OpenSSL encode command to encrypt and decrypt. And I'll demo this. All right. And then if you want to look at the manuals in Linux, you can use the man command. So you can type man OpenSSL, right? So that's the manual for Linux. And the PDF is attached, so that's also provided. So that hopefully you've started to read that material, as it provides a lot of information on commands and things like that, syntax, and so on. So you can see I have 5 problems here. And at the end, I'm asking you to submit a report showing your work and results. Okay, so encryption using different ciphers and modes. Please replace the cipher type with a specific cipher type, such as AES 128 CBC or BF CBC or AES 128 CFB. So you can see here that this type is telling you the algorithm, right? So here, these are block cipher algorithms. 2 of them, the generic frameworks are DES and AES, right? AES is the Advanced Encryption Standard. And also the 128 usually indicates the key size, right? So what it's using inside, even though your key can be smaller than 128 bits. Okay, and then if you notice at the end, this one says CBC, whereas this one says CFB. So that's the mode of operation. And that's one of the things that we will learn later on in the theory, but it's basically just how the blocks are being shuffled, how they're being, XORed, okay? So that's the key thing. And this is pure algorithm. So it's, how the algorithm works. So in this task, you should try at least 3 different ciphers, okay? So that's, I'm not very, not everything has to be very precise in your labs as far as solutions, but I'm looking that you kind of, try different things, okay? So, if I suggest try 3, please do so, right? So basically that's the idea. So you can play with, you know, the different commands and just kind of, you want to see what happens basically, okay? And you know, make a note of the information that's being created. I'm going to show you, you know, what the output file looks like. I'm going to show you how to look at the files and the different things like that. You're going to have to get used to seeing when we're dealing with encryption, a lot of like hexadecimal data, you know, it's going to look like that, okay? Binary data, basically. Any questions on number 1? Does that make sense? All right, number 2, we're going to encrypt an image. I think you'll really like this problem. It's definitely a really great problem. And because it's going to help us to really visualize, you know, how one algorithm could be safer or better than another. All right, so you're going to have to think a little bit of what's happening in the background, right? And then later on, when we discuss the algorithm, we'll learn exactly what's going on. So this is the image encryption lab, and basically we're doing ECB versus CBC. We would like to encrypt a picture, and you can actually try this with any picture. It doesn't have to be this picture. You know, students in the past have tried other pictures, and the thing is, you have to make sure use the same extension probably, because what I'm going to show you is for that type of image file, which I think is a PNG. I can't remember. All right, so, but basically we would like to encrypt a picture so people without the encryption keys cannot know what is in the picture, right? So that's the idea. We're trying to achieve confidentiality. Okay, so please encrypt the file using ECB, which stands for Electronic Codebook, and CBC, which stands for the Cipher Block Chaining Modes, and then visualize both. You will have to show both images after encryption and determine if one image encryption technique is better than the other, okay? And this corresponds to task 3 in the PDF that I attach. Everyone with me so far? You know, that's kind of just understand the questions, right? That's all I care about is I want to see these 2 images after they've been encrypted, and then you need to think, okay, why did this happen, right? You know, and so that's gonna allow you to understand how the algorithms work, etc. Number 3, padding. So here, as I explained, you know, this symmetric encryption, which means we break everything into blocks. So if, you know, in the last block, you know, we can't fill up that block with data, then we have to pad it with like zeros or spaces or something like that. So that's what you're going to play with. You're just going to look at the size of the output file, maybe try to, you know, look at the data, which is something else that you can do with a specific command I'll show you. And that's it. Just kind of, there's nothing there more than to see what happens, okay? So you're going to try to encrypt the file with several ciphers and modes, compare the results, and indicate which encrypted files have padding and which do not. So you can use ECB, CBC, CFB, and OFB modes to encrypt the file, okay? And you can pick any cipher such as AES, but you can try other ones. Please report which modes have paddings and which ones do not. The idea is that for one file, you want to determine which algorithms have padding and which do not. So what that means is, you know, you create a text file, or put a paragraph or some text in it, and then that's your experiment, right? You're going to apply all 4 techniques to that one file and look at the differences. You guys see that? Okay. All right. And number 4, corrupted ciphertext. Okay, so error propagation. All right, so how does the error propagate in the data through the blocks, right? So you could the goal here is to make a plain text file encrypted, corrupt 1 bit of it. So there's a tool we're gonna use to corrupt a bit of it. So, you know, I don't want you to change a letter. I want you to, at the binary level, just change 1 bit of it. Okay, so that's what we're gonna do. And we'll use this exercise several times throughout the semester. But the goal here is to make a plain text file, encrypt it, corrupt 1 bit, decrypt the corrupted file, and determine what happens to it. Okay. And then, as I said, number 5, this one I'll let you guys do because, you know, you should be able to do it once you've done the first 4. work with a partner and send them a file via email. So this can be whatever you want. You can make it as simple as just creating a text file or as difficult as, creating a video, whatever you want. So try whatever you want, but the simplest thing is just to create a text file with a secret message. This is a secret message. Put your name on it or something like that. How would you achieve perfect confidentiality? This is the key question, right? It sounds probably easy, but it's a little bit more complicated than it sounds, okay? How do you achieve perfect confidentiality? Can you achieve perfect confidentiality currently with what you know? So you need to answer that question. So in your report, please indicate your partner's name. And you must do this exercise and not just talk about it. It was like, like create a hypothesis and just like elaborate on what you would have done. You need to actually do it and show evidence that you did it. Okay? Make sense? Any questions? All right. So yeah, and then you submit a report showing your work and results. All right. So let's start the virtual machine. Okay, so you'll need to open a Brightspace on your VM. Okay. Yeah. Your what, sir?
Computer.
That desktop won't turn on? I don't know. Yeah, some of them may not be working, or maybe not connected properly.
Try to plug the going back in. That's how fix this one. Yeah.
Do you want to switch? I'll just monitor.
Sure.
Oh, yeah, if you have a laptop, that's cool. All right, so I'm going to log in. And also, by the way, if you had issues with your virtual machine setup and all that, I added a link here under resources. Common errors setting up the VM. So over 10 years of questions, I've collected all these in a FAQ. So you can just go there and look up your issue, okay? So click on this one. And you can scroll down to useful, and there's several sets of instructions. Or if you had errors like I can't find a name for the NAT network, click on that. Or UUID error setting up speed on VirtualBox. Click on that. All right. So these are all the errors that I've seen. So it should give you the instructions for it. Make sense? And if that still doesn't work for you, then we'll need to add a new description to the FAQ. But yeah, so usually these are the common ones. Okay. So just read through them and you should find what you need. Got it? All right, so let's go ahead and start problem number one. I think my VM is working now. Yeah. Okay, so I created a folder here on Tuesday. Right. And I'm going to, for the first problem, I can create the file. So I'm just going to do that. All right. Okay. All right. So remember, you're on Linux, right? You're on Ubuntu. Even if you don't remember how to, don't be scared by this. It's super easy. All right. And you'll pick it up real quick. So click on the terminal. There's only, you might think, okay, Linux, there's like thousands of commands, but really we're just going to use less than 20 commands, in general. Okay. So don't worry about that. I record the video so you can replicate everything. All right. So let's go ahead and get started. Okay. So what do we do first? We want to know where we are and navigate to that folder. All right. So I'm going to, so you don't lose your files, right? That's the key thing. Students, it's like, I can't remember where my homework is or on their computer. So always pay attention to where you're working. And so that's why the two commands that I use are pwd, which tells me I'm in home seed, right? The root directory home seed, okay? And then ls-l, which tells me my folder. So I usually put everything on the desktop. So I'm going to do that. Desktop. Okay. ls-l. Okay, now I created a new folder. So it should be that ITS 350. So I'm going to cd into that. As we're going to create a lot of files, especially with encryption. We're creating, we'll have like 5 files to do something, the keys and everything. So it might get you're going to fill up your computer. So I suggest you have individual folders for everything as you're working through it. Okay. So I'm going to cd into ITS 350 fall 2024. Okay. Clear ls-l. All right. So this is the first problem is we're going to try to encrypt a file. Okay. So I'm going to type this up for you guys. It's in the PDF. Okay. So you can also get those commands from there. But let's go ahead. So the idea is we want to, this is your very first encryption. This is a real encryption, by the way, not a toy encryption or something like that. So this should be somewhat secure, right? So, something you can trust. So let's go ahead and create the file. So I like to use the nano editor. So I'm going to do nano. I already have plain in there, so I'm going to use it again, plain.txt. Okay. And I wrote this is a secret message. And then I'm just going to write Thursday, August 22nd, 2024. All right, so I'm just you can put your name in here or something like that, okay? So we're creating the message. Control X, Y, enter. Got it? Questions? All right, so now if you want to look at the data, this data is not encrypted, so anybody can see it that has, read permissions, right? So there's several commands we can use. I'm just going to use this cat command, and I'm going to view the contents. And you can see it's right there. I can see the contents of it. What is the goal now? The goal is, you're here on your computer. Everything's pretty, great. You want to communicate with a friend who is on the other side of the world, right? In Japan somewhere. And so but you need to communicate securely. Remember? That's the scenario that you have to think about. So you need to send not plain.txt. If you send plain.txt, you can assume, even if you send it via Gmail, right? And Gmail is encrypting somehow, you have to assume that somebody has broken that. Okay. So you don't want to, some government can tap in and look at your file. So you need the file before it leaves your computer to be encrypted with your own techniques, with your own keys. If they don't have your key, there's no way they should be able to break it, right? So that's the idea, right? So we don't want to send plain.txt. Instead, we're going to send an encrypted version of that, a second file that we're going to generate from this one. Make sense? So that's basically the objective. All right, so now we're going to do our first encryption. All right, so I'm going to do OpenSSL. Just like that. That's the tool, the library that I'm using. I'm going to say enc for encode. Okay, so it's a long command. Then the type. So this is, I'm just going to type right here, type. That's where the type goes. So I'm going to do dash AES, that's the Advanced Encryption Standard. So that's like a general framework of how to do a block cipher encryption, okay? And then there's implementations of it. Then I'm going to say dash 128. So this is usually like the block size, okay? Some specific parameter. And then I'm going to use CBC, all right? So this is one of the modes of operation. So that means you use AES, but you can mix up the blocks in different ways, okay? So that's the basic idea. Then you can do dash E for encrypt, right? Later on, then, okay, we'll need to use dash D to decrypt, right? So that would be the idea. Dash in, so this is going to be the input file that goes in. So in this case, it should be plain.txt. You guys see that? All right, that's the input file. Then we're going to say dash out. And we're going to generate a file. And I suggest for these files, give them specific names so that you know what you're looking at. So for instance, I'm going to say cipher AES, and I'm using the CBC mode of operation. So I'm going to say CBC. You see that? And then the extension is going to be bin because these are binary files. Got it? Everyone with me? All right. But we're not done yet. We need to do something else. Now we need to provide the key. So that's dash K. Notice this is an uppercase K, and that's the key. So everything in cryptography works with keys, okay? And these keys should be what? They're sequences of bits that should be as random as possible. The bigger, the better, right? And we're going to look at some of the theory behind that, right? Okay, but basically this. Now, to keep things simple, I'm not going to use a random key, but you can try different keys, different sequences of keys. I'm just going to use a pattern. So I'm going to say 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9. And then I'm going to do AA, BB, BC, DD, EFF. Okay, and like I said, you can try other things, but this is basically the password, or the key that I'm using. It's not a password, it's a key. Some of these algorithms can also have a password, but this is the actual key. And again, as I said, we're going to learn how all this works, right? Think of it as that data is inside and the library is converted into a sequence of bits and all that, okay? The other thing you're going to see that I'm going to add here is something -IV. This is called the initialization vector, okay? The way to think about this is think of it as at the beginning, you need a block. This will become very obvious once we start coding this. When we start running like in a for loop, you'll run into the problem that what do I do at the beginning? I don't have a block. So that's going to be this block, okay? The initialization vector. So it's just so, and this initialization vector does not need to be a secret. The key does need to be a secret, okay? But it's just something to get started. So in this case, I'm going to do, this happens a lot. There's always like this random thing that algorithms have. And then there's the key, which definitely should be kept a secret. All right, so 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8. Okay, so that's basically the initialization vector. That's another sequence of letters and numbers. Okay. All right, and hopefully that should be it as far as that command. So let me go ahead and run it. Okay, we get some text. It says hex string is too short, padding with 0 bytes to length. So you can see it's actually telling you that the algorithm wants to pad this because we're using CBC. Got it? Any questions? So hopefully everyone then, now if you do ls-l, you have two files, right? You have the original file, which was of size 48. You see that? And then now you have this new output file, which is of size 64. Because things work in blocks, usually you're using multiples of a byte, right? So it's going to be 32, 64, that kind of a thing. But this is where, in terms of padding, you need to look here at these sizes and pay attention. That's it. All right. So we've created a file. Now we probably want to look at it. So remember how we could look at plain.txt, right? And that's, the message. Now we can look at the encrypted file. So it's going to be cipher, and you can tab. So to autocomplete, so you have cipher AES CBC, and you can see it looks like that. Why does it look like that? Because it's binary. You're literally looking at a sequence of binary bits, and then when they come back into the terminal is trying to create letters out of them, like it's thinking they're Unicode or something like that. Okay, so basically sometimes they'll look like strange characters, etc., but it's basically a bits. That's it. You've encrypted your file. So this is what you have to send your friend, right? In problem 5. So you have to achieve perfect confidentiality. And all you can do is send that file, the bin file, and use email. Okay? Any questions about that? Yeah, please.
On the instructions, the cipher. The beginning of instructions talks about building a whole Docker system.
Yeah, you don't have to do the Docker at all. Remember, that's just read it for your own FYI, right?
Oh, okay.
You only have to answer the 5 problems.
Okay, so and everything is built into the Docker.
Yes, Docker, you don't have to worry about Docker. Read the document, certainly, but you don't have to do everything in the PDF, right? Yes.
So say you wrote something that was more than 64 bits, would it add it to 120?
It might,
bits?
yeah, exactly. You should try it. Yeah, that's a good thing to try out. So again, guys, remember, there's a lot to read, but only answer the problems that I ask you about. Any other questions? Any other questions? All right. So let's try a few others. Let's try. So all I'm going to do now is I'm going to generate a new file from the original file, but I'm going to use a different mode of operation. So notice I'm just going to do up arrow here, bring up the previous command. There you go. And I'm going to change the output name, right? Because I want this to be a different file. So I'm going to call this one, I'm going to use CFB. So CFB, do you see that? And then here in the type, I'm going to change this from CBC to CFB. Do you guys understand? So basically we're still using AES, but we're using a different mode of operation, which is a different way of implementing the algorithm, which we will learn later on. Okay. All right. So OpenSSL, all that is the same. We do want the name to be different just so that we can compare, right? So now I'm going to go ahead. I hit enter, right? So I should have two new, another file now. And there it is. Do you guys see a difference between the files? Is there something different? What is? Yeah, sir.
The blocks for CFB is 48.
It's smaller, right? It matches the plain text file. Do you see that? So what does that tell you? It tells you maybe there's no padding, because it's a different type of the algorithm. Exactly. That's what you have to pay attention to when you're doing the padding exercise. Got it? Pretty simple, right? So today's slide is pretty simple. All right. And just play with it. You can try different combinations. Let's see. There's one called BFCBC, so I'll try that one. So I'm going to do here. Don't forget to change the name. So cipher. BF CBC, and then change this type here to BF dash CBC. Okay, and also you can try different keys, different initialization vectors. The point is to just, you know, start playing with this, right, and see what happens. Okay, so I hit enter, ls-l. You can see I now have 3, and the BFCBC has a different size even because it's a different type of an L. Got it? Any questions? Questions, guys? Nope. All right, yeah, so that's it. I mean, that's actually problem 1, right? Pretty straightforward. So we have done that one. And of course, I guess you'll want to see the encrypted versions, right? So let's look at the encrypted versions. So I'm going to do cipher AES. We did, what's the first one we did? We did CBC. So I'm going to do CFB. Linux is case sensitive, so don't forget. So CFB. Yeah. Oh, no. Oh, yeah. .bin or tab. See this one, there's the encryption, right? So got it? Okay. And of course, we want to decrypt. So that's the next thing that we're going to try. So, you know, there's no point in sending an encrypted file and not decrypting it, right? So we have to look at it. So we'll do that in a second. Then we're going to do the last one, cipher BF, okay, tab, and there it is. So we have our encrypted files, ls-l, yep. So they should be correct. All right, so now what do we want to do? We have visualized the files. Now we want to decrypt the file. So let's do the CBC one. So I'm going to decrypt cipher AES CBC. Okay. So of course, to prove that it works, we're going to create yet another file, and we're just going to call it plain decrypted or cipher decrypted, something like that. Any questions? Everyone with me? All right. So we're doing the decryption part. So OpenSSL ENC phone dash AES dash 128 dash CBC. So that's the algorithm. And then now notice dash D for decrypt. We also have to change the order of the files. So dash in should now be cipher AES CBC .bin dash out is going to be, let's just call it plain decrypted. Okay. You can say not txt. And then the key, of course, has to be the exact same key, right? You can't do another one. Obviously, it wouldn't work. So then I'm going to do 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9. AA, BB, CC, FF. And we also need the initialization vector, which was 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, all the way to 0, 8, I think. Okay, just like that. Any questions? Okay, so bad decrypt. Okay. If I'm getting, did you guys run it? Did it work for you guys? Yeah, for some of you, it worked? No? It worked? Okay, yeah, so I must have mistyped something. So I think, let's see, 0011. And if you spot something,
There
please.
are 3 sevens.
There are 3 sevens? Okay, perfect, thank you. All right, and then, so there, yeah, 2 8s, 2 9s, A, B, B, C, C. Yeah. All right, so we have to be very precise when we do this. Okay, so it seems like it took it this time, so let's go ahead. And we have a new file, plain decrypted, right? So this should be, we took plain, we encrypted it into Cipher AES, CBC, and then we took that, we sent that to the other side of the world. Then over there, they decrypted the file and they created plain decrypted, and now they are going to read this secret message, right? So I'm going to do cat plain decrypted tab, and there it is. This is a secret message, Thursday, August 22nd, 2024. That's it. So that's the whole pipeline. You use AES, CBC, that should be a pretty good cipher. Okay, so if you want to achieve confidentiality, this would be a good algorithm to use. Any questions? All right, what are some, so let's try doing this one. I'm going to change E to F, right? And I'm going to change the name to decrypted 2. Yeah, so it doesn't, doesn't know how to decrypt it. Okay. So any questions, guys? Questions? So do you think you can do problem 5 now with this, with what I showed you, and achieve perfect confidentiality? You're convinced that you can do that? You sure? It's almost like a philosophical question. You have to think really carefully about what is being asked in problem 5. So let's read through it again. Let's go back. No, sorry. Let's go back to table of contents. So let's think about problem 5, because actually, if you could say yes to problem 5 right now, then basically we could end the class like today. Like today. We're done. But maybe we can't, right? So think about it carefully. So let's go back to problem 5. And it says, work with a partner and send them a file via email. How could you achieve perfect confidentiality? By doing this. So with what you need to achieve perfect confidentiality. So you can definitely, you're going to use email. You have a plain text and you're going to write some secret in there. All your credit card numbers. Something, right? Your bank account, user and password. Okay. Everything you're going to write in there. So it's starting to get a little scary, right? So how do you achieve perfect? And you're going to send this file via email. So you know how to take a key, you know how to take a plain text and create a cipher. Then you would think I would take that bin file and just attach it, on my email and send it, which is true. But I guess I've already said that would not achieve perfect confidentiality. So what's the problem? What's the problem, sir?
Don't you also have to send them the keys?
You have to send them the key. So physically tell them the key. What do you mean by that?
Tell them, like the key itself, have them.
How would you tell them the key? They're in Japan. You're here.
Get that part, I thought we were talking about like our partner.
Yeah, well, I mean, your partner's gonna be at home. Right? So maybe you're gonna do this on Saturday and you're on Discord or whatever, right? Right. So how do you tell them the key? Because you say you have to give them the key, right? There's no way that they can decrypt this without the key. So how do you solve this? Because that's how you achieve perfect. See, you won't achieve perfect confidentiality if somebody can read the message, right? And how can someone read the message? You know, they know how to use AES, OpenSSL. They will intercept your cipher.bin. You can assume it's gonna be intercepted. Yes, sir.
The recipient is gonna have a key they give you, you use the key to encrypt the message, you give them that encrypted message with the key they gave you, and now the recipient also has a second key they didn't give you, and that's their secret key. Using both the key they gave you and their secret key, they can decrypt the message.
So they're gonna give you a key? What kind of a key?
A public key that is available that they can give out.
Okay,
Everyone needs to send them information.
and what is this public key exactly?
Some long string of numbers of some kind.
Okay,
Imagine some kind of SHA output. And
so another key.
they'll need to give you a key that you can use to encrypt, that only with their private key, they can decrypt.
Ah, okay, so you're talking about public and private key infrastructure.
Yeah.
So another technique.
Yeah.
Okay, so I'll accept that. So yes, so and that we require something like that, some kind of a mechanism. That's asymmetric encryption, right? But if you don't have that, let's assume that you don't have a special magical algorithm that can solve this problem called public and private key, which is true, you're correct. How think of ways that you could exchange that secret key without, if someone hasn't invented that, right? How do you solve this problem? Your friend is in Japan, you need to send this bin file because they're like, they need to get money out of the bank or something. It's urgent. But and you want to do it securely, achieve perfect confidentiality, but you have the problem of the key. So what are some ideas? Yeah, sure.
Try encrypting the key itself, but then you're just back to square one of.
Okay, so if you encrypt that key, that's great, but then how do you give him the other key?
Another lock.
Yeah, exactly. So how do you give him the other key? Because they won't be able to, decrypt that key. So what are the solutions?
Just being clear, the problem is trying to see how they get the key securely.
Yes, without using RSA, because there is a solution, which is what he said. Well, I mean, it gives you the reason why we need that algorithm, right? Because otherwise we have a serious problem. We want to have security, right? And we know that this works nicely. This actually works really well. But the downside of it is this K00, this thing here is the whole problem. How do you exchange that securely? We can send a bin via email, but how do we give them the, oh yeah, go ahead.
If you're just trying to do like plain text like that, there is no way to do it securely except for your RSA.
Right. Let's not use some, RSA yet, right? We'll get to that later in the semester. But so the only solutions, you should convince yourself that the only solution really is to put a person on an airplane with like a suitcase with the password in there, and they have to go to Japan, and it's like handcuffed to their wrist. And when they get there, they just give them the key, and no one else should see. And then they need to destroy it or something. Do you guys see that? It's a very difficult problem. So, you can what? You call them, but see, that's going to go over the line, right? And what if?
It's like
Your messages.
Right, but then they're using encryption. So you're building this whole infrastructure. I get that. Like, let's just use Signal, right? And send a password through Signal. But then they're doing the encryption for you. Yeah. Yeah. That's true too. So, you work for some government agency, you meet like in a basement somewhere and you exchange the key right there, right? And then that person needs to leave knowing that. Do you see the problem? So yeah, exactly. So otherwise, you know, we have to do that like physically, you know, get together in a coffee shop and exchange this key. But that doesn't work on the internet, right? So let's say you guys want to go shopping on Etsy. You've never been to Etsy, right? I mean, some of you may have, but let's say some of you haven't been to Etsy and you really want to buy something on Etsy. Etsy is, let's say, I don't know where they're at, but let's say they're in Seattle. You're not going to get on an airplane, fly to Seattle, get the key, and then come back and start shopping, right? So there's got to be another way of solving that problem. So that's what later on, like in week 3 or so, week 4, we'll start getting into the asymmetric algorithms. And as you said before, you know, we're going to try to understand how we can, all that stuff that we're going to look at, a lot of math and code and a lot of things, just so that we can send that key securely. But that's really important. Okay? Make sense? So yeah, so that's the problem 5. So as you can see, still please go ahead and exchange the message via email. You can send the message, but you know, what are you going to do basically for that? Let's say that, you know, you do your homework in your home and then you're sending that file to your friend. How are you going to exchange the key? So basically you'll probably just attach it to the email, but then you should know that by doing that, that's insecure, right? Even if you send it to through a second email, that's still insecure. You know, the people that are trying to steal this information are very good. So you're not going to trick them by sending 2 emails or anything. It's insecure, right? So you have to achieve, when I say something like perfect confidentiality, that means you have to do this exactly right? And the only solution will be asymmetric algorithms, okay? And they work. I mean, they amazingly work. So your answer for this should be that you can't, okay? If for problem 5, you cannot achieve perfect confidentiality right now, okay? Any questions on that one? So it should be pretty easy. Still, go ahead.
Interceptors are really desperate to help us with our homework and just intercept these keys.
Yeah. So, but hopefully that makes sense, right? So this is the first problem. It's meant just to kind of motivate the challenges of key exchange, etc. All right, great. So we've done one problem. Right? So you can play with it. In this task, you should try at least 3 different ciphers, encrypt them. I think you have done, you understand problem 5. So just find a partner, write a file, encrypt it with and just send it via email. And just be aware, you have to put the key there probably, and that means you don't achieve perfect secrecy. Yes.
So I just have 2 email clients next to each other, 2 separate ones. Guys, one client to another, and that's my partner.
No, please work with someone, because later on it gets, as you actually brought this up, right? So you're going to have to use public and private key. So when you do that, you're going to have a public and a private key. You're going to have a public and a private key. And the thing that I've noticed when students just do everything by themselves is that they confuse the keys, because all 4 are there. So they don't actually understand like which one they need to use in which situation. Okay, so yeah, so this is a very common mistake I see. So I've, over the years, made it mandatory to work with a partner. That's because I could see when they work with a partner, nothing worked, because they didn't really understand which keys to use. Got it? Yeah. So definitely do that. And you know, it's for your own benefit. All right. So I think we can move on to problem 2. And don't worry if we don't finish these problems, although I think we'll finish them today. You know, we can always finish them on Tuesday. But let's do problem 2, which is the image encryption, okay? So for this one, you need to go to Brightspace. So open up Brightspace on your VM and download the files, okay? I think I should have them already. So I'm just going to move them to my... So I really just need this image, I think. So I already downloaded the file, so I'm just going to move this. And notice how, this is what I was saying, really quickly, this starts to fill up with files and it's going to get pretty confusing. So I'm just going to create a new folder here. I'm going to call it block ciphers. All right. I'm going to throw this image in here. All right, that's the image. It is a BMP, actually, a .bmp extension. So the technique that I'm going to show you right now is specific to this type, all right? If you want to do this with JPEG or something, you got to figure it out on your own, right? How to do it. The different images have different formats. So, but basically the idea is we're going to encrypt the image, right? That's it. So we're going to encrypt that image. It's just data, but the problem is there's two types of data in this file. There's metadata, and then there's the actual image data. So I believe for the .bmp image, the first 54 bits are metadata. And what that means is that when you open a BMP file in a BMP editor, etc., it needs those 54 first bytes to understand how to render the image, okay? And then after that, after 55, then you have the actual data of the image, like the colors, the red circle, and the blue square. Do you guys see that? So if we just encrypt the whole image, what's going to happen is when we try to open it, the editor won't be able to read those first 54 bits, right? And so it's going to not understand it, won't be able to render the image. Got it? So what we need to do is we need to take that, break it in parts, not encrypt the metadata, and only encrypt the data. So that way, when we visualize it, we'll be able to actually see the encrypted image. Okay? Does that make sense? Any questions on that? All right. So that's what we're going to try to do. Okay? So I already have the image in there. So I'm going to go ahead. I'm going to go back to my virtual machine and raise your hand if you have a question. And this should be a very fun exercise, I would think. I really like this. It's like, very nice. All right, so I'm going to go ahead and take a look. Just always checking where I am. So I'm going to go into this new folder, block ciphers. Okay, I'm in the folder. I'm going to hit clear ls-l. There's my image, pick original, okay? So I should be able to visualize this. So if I go to desktop and I go to fall 2024, block ciphers, there it is. I can double click on it and it opens, right? So this, I'm visualizing the image. Okay, what I want to do is encrypt that data securely. So we're going to use, let's see, we're going to use AES, okay? But AES is very secure, right? But remember that you can use different modes of operation. So that's, like how you're jumbling up the blocks, and ECB is one way of doing it and CBC is another way of doing it. So what I want you to answer in this question is there any evidence that one is better than the other, right? What do you see? And so you need to like think about this one, okay? So let's go ahead and do that. So let's go to the terminal. I'm going to start generating some files, okay? Using OpenSSL and all of that. So first of all, I'm going to split the image into header and body. So that's what I explained to you, right? So it's going to be the metadata and then the rest of the data. So to do that, we can use the following command. So I'm going to do head-c 54. So that's just going to grab the first 54 bytes, I think. So I'm going to do 54. And I'm going to say the name of the file is pick original, right? So I'm going to do pick original .bmp. And I'm going to write this out into something called header. So I'm basically, it's like I'm slicing that data and putting it in another file called header. Okay. And that, remember, I don't want to encrypt header because otherwise I won't be able to look at the image. The whole thing is encrypted. Okay. All right. So no errors. I do ls-l. There it is. Notice that it does have, in fact, some data, and it's 54. Got it? All right. Now we're going to do the same thing. I'm going to use tail dash C, and I'm going to say plus 55. Okay. Pick underscore original dot BMP. Oops. Got it? And I'm going to write this out to body. Hit enter, ls-l. So I got the body and the header. Notice that body and the header. Notice that body is big, right? It's a big image. That's the data itself. Okay. So now what we want to do is we've looked at the, both of these files. Okay. Questions? So now what we want to probably do is we are going to encrypt the body twice, right? We're going to use ECB and also CBC, because the whole point of this is to look at both modes of operation and try to determine if one is more secure than the other. Do you see that? So we're going to encrypt both bodies. So you have to keep track of that. What do we use? Currently, all we know how to use is OpenSSL. So that's what we're going to use. So I'm going to do OpenSSL. Encode. I'm going to use, now keep in mind, AES -128 ECB, the electronic codebook, right? ECB. Okay. We're going to encrypt, so -E -in, and the input to it should be body, right? Okay, the data itself. Now the out, that's going to be body underscore ECB dot bin. Okay. Right. All right. So that's what I'm doing. And then as far as the key, you can just use the same key we've been using. So 001, oops. 0011 22 33 44 55 66 77 88 99, and then AA BB. No, it's 3 B's. B. C C D D E E F. And then the initialization vector as well. So we're using the same approach. 01 02 03 04 05 06 07 08. All right. So that should be it. Okay. And some ciphers don't need initialization vector, right? So like if I hit this one, warning, initialization vector not used by this cipher. And that just is because of the way the algorithm works, right? So in fact, we need an initialization vector in a sense to make the algorithm more secure. You see that? So you can start to think about it that way. So I'm giving you a hint here, right? All right, so I've done it, hopefully. And there it is, body ECB .bin. So it is now encrypted, basically, okay? We've encrypted that data in some way. And then later on, we have to, so how is it being done, right? So we have to start learning about XOR operations and all that, which is, the topics we'll start covering on Tuesday. All right, now we're gonna repeat this process. For CBC, okay? So I'm gonna use CBC, so I can just up arrow, and I'm just gonna change some parameters. So I'm gonna do OpenSSL encode AES 128, but instead of ECB, I'm gonna use CBC. So CBC-E. The input is still body because that's what you're encrypting, right? The image, the squares and the rectangles. The out now, we want to change the name. So this one is going to be cbc.bin. Same key, same initialization vector. Notice this one doesn't say anything about the initialization vector because it's using. The algorithm is different. You guys will have to implement this algorithm. This will be one of the problems that you'll have to do later on in the semester. Guys, questions over there? Any questions? So now that I have this, let's take a look at the file. So I'm going to do clear ls-l. I've got both of these, and I've got the header. And again, the header will not be encrypted because that part needs to be available to the image viewer, right? So that it can interpret the data, which is metadata. So now what we need to do is we need to concatenate the header and each of these bodies to create the new image that we're going to visualize. Right, and that's pretty straightforward. We can just do here, we can use cat to concatenate. So I'm going to do cat header, right? That should go first. Header. And then I'm going to do body underscore ECB dot bin. And then the output, we just need to give it a name. So I'm going to call it pick underscore ECB dot BMP. Make sense? Okay. All right, there we go. And I'm going to repeat the exercise. And I'm just going to change this to CBC. And of course, this should also be changed to CBC. All right, that's it. So we've done it, hopefully, right? We have our two images. The body of it has been encrypted, but one was encrypted with ECB. The other one was encrypted with CBC. All right. So we can look at the files, and now we can proceed to view them. All right. So I'm going to go ahead and go back to the desktop. And here they are. So I'm going to look at the original one first. There it is. That's the unencrypted image. Now I'm going to look at the ECB image. That's ECB. Do you guys know how to make this bigger? Oh, here, maybe. Yeah, perfect. So what do you think? It's been changed, right? The encryption algorithm did this. So what do you think? Is it a good encryption or a bad encryption? It's bad, right? Why? You can still kind of make out the original. Exactly right. And then we're going to learn later on that, the definition of a good cipher is that you cannot tell anything about the original from the cipher itself. Do you see that? We're going to, start defining what makes a secure cipher. We can tell we can tell there was a square there and a circle. What if that's like the strategy that, the circle is a city, and then you're going to attack from the square? That's very valuable information still, right? It's right there that the attack is coming from here or something like that. Got it? Do you see that? So that's really important because this example shows you that ECB is not actually as secure, even though it's being used within AES. So why does this happen? This is something that we're going to have to get into the algorithm right? And just kind of figure out why, even though it's a robust algorithm, it does have this vulnerability basically. Got it? So then the problem is, how do we make this better, right? So what can we do? So that's where CBC solves the problem, right? And then so we have to understand how that algorithm works. Why does that solve it? All right, it has the initialization vector, but it's got something else going on, right? And so these are the topics, again, that we'll start discussing next Tuesday. But we can, at this point, look at the output of CBC, right? So we want to look at CBC. So this pick CBC, that's your image. There it is. Sorry. All right. What do you think about that? That's the same pick original, but it was processed with a different mode of operation, which was CBC. And this is the encrypted version of it. What do you think about this technique? Why? You cannot make it out at all. It almost looks random, right? Like you almost think this is random. And that's the goal basically of cryptography, right? You want to make things look random. No pattern should be there, because if there's a pattern, then that's called cryptanalysis. And that just means somebody is trying to like figure out, I can see this or I can see that and I can break this. You don't want them to break your ciphers. Okay. Any questions? So yeah, so this is a great exercise because it shows us what we want, even visually, right? And it shows us what we don't want, which is the other algorithm, because we could still make out the square and the circle. And we've used AES, OpenSSL, but just that choice of ECB was weak. If you see somebody that's trying to set, telling you, Ellie, let's use AES, you got to be very careful, right? In what they're doing, because they might be leaving vulnerabilities in there that they can still make out, what you're sending. All right, any questions? So this is basically problem 2. I would recommend that, this is what you have to submit, because like I said, I'm demoing and showing you how the lab should work. Basically, then you need to provide screenshots of both of these images. Hopefully that's obvious, right? You would show this one, the other one, and you would say, as you said, because you can still make out the original, then that's insecure. And that was ECB. Yeah, please.
The first question, what do we provide as an answer?
Oh, yeah, what's the first question? The first problem was you just need to try, this is the very first thing we did, so just try 3 different techniques, possibly the same ones I use.
Do we on what we submit, what do we include? Do we submit the files?
Yeah, it's screenshots. Yeah, show a screenshot of like maybe the 3 ciphers, like the output, like the 3 bin files. That's a good question. So if we go to the terminal, so I think it was, oops, sorry, last dash L. So you can just like highlight, I think it was these, right? So you can highlight that. I did the cat, and I did this, right? I did cat cipher BF. So I did that to show the output of it. So, you just show evidence that you did it. Is that clear? Okay. Yeah. So that's what I'm asking you to do. It's encryption. So some of these are, it's hard to visualize sometimes, right? Not everything is going to be as nice and neat as the pictures. Some of them are just going to be text, hexadecimal things. With the padding, it's just the numbers. I mean, so. Yep. Did you guys try problem 2? Following along? Were you able to do it? Do you have any questions about it? Any questions? All right, no questions. Well, you don't have to do more on problem 2, but in the past, some students have just tried different images, other BMP files, just for fun. Play with this. These are powerful tools, and you can try out more things. Okay. All right. So yeah, let's go back. Okay, so I have, as I said, that's the random image. And then And then this was the other image, the insecure image, and we've seen that. Okay. All right, so now let's go back to the Word document. So we've completed problem 1, we've completed problem 2. Yeah, so show both images after encryption and determine if one encryption is better than the other. So you should be able to answer that question now. The better one is CBC. Padding is very straightforward. So I'll go over this one. Encrypt a file with several ciphers and modes. Compare the results and indicate which encrypted files have padding and which ones do not. So use ECB, CBC, CFB, and OFB modes of operation to encrypt a file. And you can pick any cipher. So I recommend you try different ciphers, try DES, try other things. Please report which modes have padding and which ones do not. The idea is that for one file, you want to determine which algorithms have padding and which ones do not. So this is very easy. I'm just going to create a text file. I'm going to put some text in it, and then I'm going to encrypt it with 4 different modes of operation, the ones that are listed here, and then look at the size. That's it. We've done this already as we've been doing other problems, but now this one's specific exercise. All right, so let me try to do that. All right, so we'll go back to the terminal. I'm going to hit clear here. Now, yeah, I'm going to go into block ciphers. All right. So I'm going to create a new file. I'm going to call it padding problem .txt. Okay, and I'm going to say okay. Actually, I'm going to do it like this. A, B, C, D. Then remember that uppercase and lowercase in the ASCII table are actually different numbers. So it's important. A, B, C, D, E, F, G. Okay. You can also do numbers. And so on, right? So, we have, these are all different. All right, so I've created a file of a specific size. Hopefully, it's not like a multiple of 8. I don't think it is, but it could be. All right, so let's do this. And it's 63, so that's an uneven number, right? All right, so now, and let's go ahead and try padding maybe. And we can try different files. I just made that up right now. Right. So once again, I'm going to keep encrypting. I should have this now, so I don't have to type the whole thing. Just going to modify the OpenSSL command. There it is. So I'm going to use OpenSSL encode -AES 128 CBC. Okay, there we go. And then -E dash in is going to be that file. So padding problem dot txt dash out. I'm just going to call it F1. Actually, like one. So F1 underscore CBC, right? So CBC mode of operation, and then dot bin. I'm using the exact same key dash K, and we have an initialization vector. So, okay, ls dash L. So the F1, we're looking for F1 CBC, and it's 64. The original was 63. This one's 64. You guys see that? All right. Then I'm going to repeat the exercise with the other 4 modes. So this is gonna be ECB. Electronic code book. F1 ECB. So in this case, notice it did that, right? So 64. Okay, so pay attention to that. Let's try CFB. There, here. CFB. B. Okay. ls-l. So CFB, the bin file, notice it's 63 like the original. So that tells you something. Everyone with me? Yeah. All right. And then right now I'm just showing you like what you should do as far as the commands. And then I'm going to show you that maybe try different files of different sizes just to see everything that happens. So the last one is OFB. Yeah, OFB. So I'm going to do this one here. B. That's a 0, OFB. Okay. And then ls-l. And OFB also has 63. That's the original instead of 64. So just by looking at this, what would you say? Like, what would you conclude? It seems like 2 of them use padding and 2 of them maybe don't use padding, right? All right. To further this experiment, you can try different files of different size, right? So for instance, I'm not going to do this part, but what I'm going to say is kind of repeat what I just did for these 3 new files that I'll give you. So we did everything on F1. Now I'm going to do F2, F3, and F4. Okay. And just repeat the exercise. And then write down your observations. It's kind of all I'm saying. It's experimental. All right. So we're going to repeat. I'll show you how to create the file. So if you want to create a file of a certain size, we can do something like echo -n, and then in double quotes, you can just write 0, 1, 2, 3, 4, right? So you write these numbers, and then you're going to redirect that into f2.txt. Everyone with me? Okay. Hit enter, ls-l, and you did F2, and notice that basically is of size 5. Okay, so then you would repeat, you would encrypt that file F2 with all 4 modes of operation, and then note your results, basically to do. I'll do this a couple more times. So create another file. This one, we're going to call it F3. And this one will have will go all the way to 9. So 5, 6, 7, 8, 9, just like that. Okay. Go ahead. Now ls-l. That one is of size 10. Right. And so again, you'll encrypt and just make a note of, which ones have padding, which ones don't. And then finally, do one with even more. Echo, call this one a 4. So that's going to go all the way to 9 and then A, B, C, D, E, F, just like that. Right, ls-l. And that's F4 has size 16. That's a nice 2 bytes there, so you can play with it. Any questions, guys, on what you have to do on problem 3? All right, great. So that's what time is it? It's 5:30. We're gonna do one more thing. I encrypted F1, right? So now we're gonna look at something, and unfortunately, yeah, you know what I'm gonna do? I'm gonna encrypt F1, or sorry, F2, because I just want this to be a little bit more noticeable. So, and I think the way that the first file I used was not very noticeable. So let me try this. So I'm going to repeat the exercise, but with F2, okay? I'm going to do so F2. So the first one is going to be, so we're going to do CBC, CFB, OFB, and ECB. So I'm going to start with CBC. And this one is going to be CBC. Okay, right? Am I missing something? So CBC, the output is CBC, and this is file F2. That means the input has to change, right? So it's going to be F2 TXT. Right? Okay. Done. ls-l. So now I have my F2 CBC. There it is. It's size 16. Why is it size 16? Did I miss something? Okay. Let's try ECB. F2 ECB. Okay. F2 is also 16. Now let's try CFB. Okay. 2 CFP, right? What does that one look like? Okay, so F2 CFB, 5. More obvious, right? That no padding seems to have happened. Anyway, I think that's enough. We got enough. So now, now we want to look at the encrypted files. And we have a tool called, it's a hex dump basically. So we're gonna take a look at what's in those files at a hexadecimal level. So for that, we're going to work with F2. I'm going to write it down here just to remind myself. Okay, so I'm working it with F2. So that we have a nice command called XXD. That's actually a program that we're going to use. I'm going to run first the original F2 txt. Okay, that's the hex dump of that file. Got it? That's the hex dump of it. So it's basically our 0, 1, 2, 3, 4. It's these things like here, 30, 31, 32, 33, 34. If you notice, there's a 30 followed by a 31, followed by a 32, followed by a 33, followed by a 34 in sequence, just like we have 0, 1, 2, 3, 4 in sequence. Why? Look at that ASCII table that I gave you and your answer will be there. Okay. So that's the unencrypted file. Now let's go ahead and start looking at the encrypted files and see what behavior we find. So I'm going to do, so you guys can help me out. So I need to do F2. What was the name of the first one? I think it was CBC, right? That was the first one we did of the three. Oh. Oh, bin. Was it bin? Yeah. Hold on. F2 CBC bin, yeah. And that's the encrypted one. So now, that's the encrypted data that we see. Now we probably have to decrypt this. So I'm gonna do, and I know we're running out of time, but hopefully I can just do this one. I'm going to go ahead and decrypt that same file. Okay, so I'm gonna do up arrow. Okay, so really quick here. This will be the last thing we do today, bro. OpenSSL. So I'm gonna do the CBC one, the one we just looked at. CBC, right? AES 128 CBC. Since I'm decrypting -D, in will be what? F2 CBC, correct? Dot bin. I think. Dash out, we're gonna do, this is gonna be a text file now, so I'm gonna say F2 CBC padded. I'm gonna say that. It's a new name. And the key should be the same, the IV should be the same. And then here I'm gonna add a new flag, -notepad, like that. Okay, it did it, right? So ls-l, CBC padded is right there. Do you guys see that? Now, F2 originally was 5. Do you guys see that? That it was 5, right? Then we encrypted it, F2 CBC, and it became 16. Then I decrypted it, and it gave me, which is this one, but it gave me back 16 again. It should have been 5, right? Is what you're probably thinking. But, and that's true, except that I used that notepad flag here. And that's just to show the padding on the unencrypted file in theory. See where I'm going with that? So now I'm going to use my XXD. I'm going to do F2 CBC padded dot txt. There it is. XXD F2 dot txt, right? Yep, perfect. What's your observation and your conclusion? You're looking at it at the hexadecimal. Yes, sir.
Yeah, I think so. Always have whatever's encrypted in the 16 byte blocks.
Okay, yeah, that's very good. So the blocks are defined, right? So, and it's gonna use these sizes. Here you also see that it did, this actually proves to you that it did padding. So there's the 30, 31, 32, 33, 34, right there. And then OB, 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 OB. You see those OBs there? That's the padding that I left in there, and we're looking at it at a, you know, at the hexadecimal level. Make sense? Again, this is just for you to get a better understanding of the algorithms, to kind of visualize them and motivate some of the things that we're going to be looking at later. All right, so it's 5:39, so we stop at 5:40. I would consider problem 3 solved, right? You guys can repeat the exercise for all those files, use XSD, just kind of use that as an additional tool to convince yourself of the padding and all that. There's no real, you know, I just want you to make an observation and start thinking about it. You know, we'll spend, you know, all semester just going really deep into a lot of these things, right? All right, yeah, hopefully that made sense. On Tuesday or something, I will finish the last problem. It's actually a fun one, but I would consider problem 3 solved also for you guys, for your homework. And then I will pick up on problem 4, corrupting the ciphertext. All right, have a good, yeah, go ahead.
Will this lecture be on online tonight?
Yeah, I will, maybe tomorrow, but by tomorrow for sure. Yeah.
All right.
All right, so we'll stop, give me a sec. We'll stop here for today. I will end the session right now.